Matt Vinopal. So Matt joined Ayres Associates in 2000, and his specialties include Lidar, photogrammetry, field survey, project design, flight planning, and customized spatial data services. Matt personally oversees all Lidar projects from start to finish, maintaining oversight on all project requirements and ensuring accuracy expectations are met and deliverables are complete. Leading Ayres Associates' talented team of Lidar processing technicians, Matt has undertaken the responsibility of understanding a variety of nationally recognized accuracy standards that are applied to Ayres Lidar mapping projects. So without further ado, here's Matt presenting on UAS Lidar imagery collection for the GIS or mapping professional. Take it away, Matt.
Can everyone see my screen and hear me fine?
Yes.
Sounds good. First off, I wanted to take the chance to thank WLIA. I've had a chance to, over my career, attend quite a few WLIA events, and this one continues to amaze me as far as the content of the material and the quality of the speakers and stuff. So once again, thank you WLIA for the opportunity to speak at this conference and learn from a lot of talented individuals. So obviously everyone can see my title screen. We're going to talk a little bit about UAS Lidar and imagery today. It's titled specifically for the GIS professional, but along with that, we are going to jump into a little bit of airborne Lidar as well as photogrammetry. So goal of the presentation, you can read that on your own. Data collected from UAS will be compared and contrasted to other aerial platforms. I'm going to do my best to distinguish between Lidar and photogrammetry, and then really, how each application is best utilized for the various project types, different types of accuracies, different types of projects overall. So mapping technology, I think all of us on the presentation today, all of us on the call, often hear this question, what's the right type of technology to apply to the project I'm looking at? So depending on, what your project deliverables are from an accuracy standpoint, both vertically as well as horizontally, you have to ask yourself, what sensor, what platform, what technology am I really going to apply to my project in order to yield the best results? So photogrammetry and remote sensing, typically with these technologies, you're dealing with, one of three data sets, and you could probably add a fourth to this as well, with that fourth being survey data. But generally, you're focusing on planimetric mapping, and a lot of times when I say planimetric mapping, I'm referencing 2D horizontal representation of mapping features. Elevation data comes in a lot of different formats. Field survey, Lidar, which is one that obviously we're here to talk about today, but one that's kind of dominated that landscape probably over the last 10 to 15 years. And then that final deliverable on most projects is that orthomosaic, or that imagery backdrop that helps people better interpret what they're looking at. The screen capture that I've included there, kind of below that, is a recent UAS Lidar imagery project that we flew. It was for a construction company in Michigan. And you can kind of see, I thought it was actually pretty interesting because the site had a little bit of small amount of snow covering it. So we were very interested to see how the Lidar sensor performed in this type of environment with cold weather conditions, as well as snow on the ground. But kind of gives you an idea what that site looks like. So photogrammetry and remote sensing deliverables, that blue target in the center there is really how I like to look at the different technologies. I like to say, what is that final deliverable? Once again, is it a GIS deliverable, Esri geodatabase, or is there, elevation data set associated with it? And then from there, I'm going to take a look at one of the 3 to 4 technologies to deploy to kind of meet those project deliverables. Obviously on the left, we'll start with the drone technology. You're able to get orthomosaic, planimetrics, a raster DEM, or some form of surface model. Photogrammetry also allows for the development of those products as well. Photogrammetry typically years past was only applied to manned aircraft missions. Obviously now we're applying that technology in regards to drones and UAS. Airborne LiDAR from the standpoint of elevation mapping is kind of, like I said, dominated the last 10 to 15 years. And typically, when I say airborne LiDAR, we were probably looking at data sets in the 1 point per square meter to 2 point per square meter resolution. And then mobile LiDAR, I won't touch on that one today, but that's obviously something that needs to be taken into consideration also from an engineering and design standpoint. So, and the conversation, if you look at this diagram, the conversation gets a lot more confusing and a lot more convoluted based on your vertical and horizontal accuracy requirements. You really, the factors you have to ask yourself, what type of accuracy am I looking for in regards to LiDAR? Point density, am I trying to do any type of feature extraction from that LiDAR point cloud? What's my final deliverables? As you kind of, I guess, work your way around this circular diagram, there's a lot of different information, different factors that you need to take into account, before you decide to deploy a specific technology. Because really, each one kind of has its niche, and I guess the main thing is a lot of these are starting to get fused together now. There's starting to be a lot of crossover between whether it be photogrammetry from a drone, photogrammetry from a fixed wing aircraft, LiDAR from all different platforms. And then the one point here that I like to make that is probably not discussed enough is your survey control network that you're establishing early on in your project, because really that's going to help determine the vertical accuracy that you're able to achieve with your final deliverables. So vertical accuracy standards, I'm not going to delve too deep into this, but ASPRS has a standard set of vertical accuracy requirements that they point to, and Ayres as a company points to for all of our projects. Elements that go into that, you obviously have your ground control point accuracy, any aerial triangulation factors that also need to be taken into account, any independent checkpoints that you're also collecting as part of that project need to be factored, and then a final report really denoting the accuracy of that project and what were the final deliverables and how we're able to test and validate those deliverables. So an example photogrammetry project, this was a project we completed for Minnesota Department of Transportation. And I'm not going to read through every element of this, but it kind of gives you an idea, the derivative products that can be created from photogrammetry. Also takes a look at some of the advantages and maybe disadvantages to this specific technology. I think that's the one common message I've heard probably in the last 5 to 10 years is that some people are starting to confuse, LiDAR with photogrammetry and, LiDAR with field surveying and kind of, confusing what each is. Accuracy assessment on this project. This project was a little over 30 miles long. There was a manually stereo compiled planimetric and DTM component to the project, as well as an ortho mosaic. Gives you an idea of the number of initial survey control points that were established as part of the project. I think on this we had about 84 survey points. I don't believe they were differentially leveled. They were just traditional GNSS. But then there was 128 independent checkpoints that were collected that the surface model was tested against. So it gives you an idea of the vertical accuracy spec for this specific photogrammetric mapping project, 1/4 of a foot vertical accuracy, and then 1/2 a foot at 95%. So manned aerial LiDAR, this is probably the one form of LiDAR that everyone's extremely familiar with. Wisconsin has been, pretty progressive in, the counties, municipalities, the state kind of all working together to get a statewide coverage of aerial LiDAR across the state. What you're looking at on the screen is most of the state has 1 to 2 point per square meter LiDAR. I'm not sure if everyone on the call today had a chance to see Zach Nino and Rob Mary's presentation on high density aerial LiDAR in the Milwaukee County region yesterday. That project was a project that was collected at 30 points per square meter and really showcased the differences in the point density and resolution, as well as the vertical accuracy. This gives you an idea kind of when you're looking at the, that countywide 2 point per square meter project and what that looks like from a resolution standpoint. And then if you were to compare that against a 30 point per square meter manned LiDAR collection, you can see that 30 point per square meter data set is really starting to look much, much more like an image at this point. So another example of that from another project. So in addition to the Milwaukee County 30 point per square meter project that Ayres was able to work on, we also had a project in Minnesota, Goodhue County, Minnesota, that was also a 30 point per square meter project at the county-wide level. And really, these types of projects really don't exist nationwide. They're kind of, they're one of the first projects of this resolution at a full county-wide scale. But you can kind of see the differences. Once again, if you look at that QL2 and the level of detail, you're able to see within that raster bare earth model. And then if you compare that same area, so the raster on the left is a 1 meter pixel resolution. And then on the right, you have a 1 foot pixel resolution. So that increase in point density translates to improved resolution on the bare earth surface model. I'm going to start to work my way through this. The accuracy assessment. This is something that Ayres provides on all of its projects, whether it be a county-wide LiDAR project, a project for a municipality. And then we're starting to provide these on our UAS projects as well. Big thing that we like to point out with these vertical accuracy assessments is the date of the acquisition. That's one thing I hear often is, when was my data flown and when was it collected? So, acquisition date, the units of the data, a lot of that metadata information is contained within that accuracy assessment report. In addition, you can see on the right, the number of survey checkpoints that are collected in each of the different land cover types, as well as the corresponding 95% confidence levels of how those survey values compared against the LiDAR itself. Just some field photos of those independent survey checkpoints that are included as part of those reports. Accuracy assessment on a 30 point per square meter project. And once again, I don't want to read through all the statistics on this, but as you increase the resolution, so you go up to that 30 points per square meter, the vertical accuracy also increases. So instead of 10 centimeter RMSEZ, now we're working at 5 centimeters or less in regards to the vertical accuracy. Once again, here's that Goodhue County project. Goodhue County is approximately about 1,000 square miles. So if you think about it, 1,000 square miles of 30 point per square meter data. The full data set, the classified point cloud, was 10 terabytes worth of data. So, it was an extremely challenging project to manage just from a data standpoint. But from the manned aircraft side of things, in my opinion, this is where the industry is going. It's going to more of a, county-wide, large area collection at extremely high resolution. Here's the accuracy report associated with that Goodhue County project. So you can see, the different checkpoints and the different land covers and how those checkpoints tested out against the bare earth surface as well as the classified point cloud. So UAS. UAS is really, in my opinion, one of the top 2 or 3 growing technologies within the geospatial community. I think in the last 2 to 3 years, there's been so much growth within this technology from various sensor platforms, the sensors themselves, and then the ability to fly longer, to fly at higher point densities, to capture higher resolution imagery really has been a kind of a game changer from a survey and mapping standpoint. So UAS Lidar, there's an image of the system that we deploy. I should say one of our systems that we deploy. It's the system that actually has the Lidar sensor and the camera on it. Ayres adopted the use of UAS technology from right from the very beginning. We don't use it on every project necessarily. It has to be the right fit. It's kind of a tool in the toolbox, so to speak. A lot of our aerial platforms carry a variety of sensors, whether it be digital cameras, a Lidar sensor, capturing video. So, the sensor itself, we fly some smaller platform systems as well that obviously we're acquiring either video or imagery, but this is the Lidar platform itself. Oops. So our flight crews and pilots are really trained in specializing in this technology. The one thing, we like to use our UAS systems as a tool, as I mentioned. Like I said, the project has to be the right fit, I guess, if we're going to be using it on, site type projects. This Lidar sensor, it's not a system we're going to be flying at, an entire county or necessarily an entire city for that fact. Gives you an idea of what the system looked like. You can kind of see the offset oblique cameras right there. They're 220 megapixel Sony cameras with a Regal Mini Vux 2 Lidar system. Gives you an idea of some of the equipment associated with that. 120-degree field of view. The Lidar sensor itself is able to the 200 pulses per second Lidar system. The big thing in regards to UAS that a lot of people in this space, the drone space, are not, I guess, recognizing is the positioning system of the UAS. What type of IMU and what type of antenna are you using? The GeoQ TrueView 620, our system, we have an APX, or we have a Planix positioning system as well as an APX 20. So there's a look at the battery setup and the charging station that we have with our system. Really, some of the key services associated with this, obviously LiDAR and topographic mapping, photogrammetric image collection and processing, and then the one that we're looking at a little bit more now is obviously inspection and flight monitoring. Some of the different applications: volumetric calculations, as-built surveys, bridge inspection, right-of-way pipeline inspection, transmission and distribution has been a big one for us. Cell tower mapping and inspection, so on and so forth. GIS data collection goes without saying. Really that's could apply to any of these different technologies. But that intensity image on the left there that came from one of our first test flights in the Swamico area north of Green Bay. You can kind of see the environment we were testing the system in. Extremely low line, wet, dense trees, a lot of low grass. Really, we wanted to see how the system performed in this type of environment and how we were able to penetrate that vegetation. So capabilities. Capabilities of from what we've seen from the Mini Bucks 2 at this point, we're able to achieve 2 centimeters or better on hard surface land cover types, able to create a point cloud that is capable of generating 1/2 foot to 1 foot contours. Feature extraction from the stereo imagery that we're able to fly allows for, when I say feature extraction from stereo imagery, obviously those planimetrics are not being digitized off the orthomosaic. They're actually being digitized in 3D to remove any horizontal displacement that you might be getting with that 2D extraction. Ortho imagery at a 1 to 2 centimeter GSD. And one of the big questions that I get asked is, well, how big or how small does the project have to be in order to use this system? So at this point, we've seen requests from a few acres up to 1.5 to 2 square miles. Whether or not if you get up in that 2 square mile range, whether or not it's economical to fly with this system, I think that probably remains to be seen on the site. But from a data size standpoint, we're able to actually, that's probably the limit. I would say 2 square miles. Gives you an idea. This is that Swamico site that I was talking about, north of Green Bay. What it looks like. You can see on the top, you have a nadir view of the data, looking at the Lidar swaths, each one colorized appropriately. And then on the bottom, you actually have a profile in some of the highly vegetated areas that we were testing the system in. So you can see with our system, you're getting 5 returns per pulse, and the number of returns and how that affects the representation of the tree canopy, how that affects the representation of the ground surface itself. That level of detail is extremely high in this type of environment. Once again, that Swamico area, on the top, I have the Lidar point cloud displayed by intensity. You can kind of see, so intensity is that strength with which that pulse of light comes in contact with the object that it touches. From that, you can display the data by color or by black and white. And then you have the profile view once again in that same area. And everyone that's on this call is aware that a Lidar point cloud starts out being unclassified. We wanted to see, testing of some of our algorithms for filtering out the ground, how it performed just in an automated fashion. You can kind of see the orange points there are kind of showing the ground surface and how we were able to kind of filter that and pull that information out of the data. This is another site. It's a Hastings Way site near Green Bay, or excuse me, near Eau Claire. We flew this for a transportation type application. And you can kind of see on the top, you have 2 Civil 3D surface models. One on the left there, kind of a little bit zoomed further out. And then as you zoom in on the right, you can kind of see the level of detail on the road. The one thing we like to do, we're not using the Lidar point cloud to necessarily generate the TIN model itself. What we're doing is in these scenarios for transportation applications, we'll go in and extract brake lines along the road edge and on the center of the crown of the road to help build that TIN model. We drape those brake lines to the Lidar point cloud. Then on the bottom, you can kind of see the colorized point cloud on the left, colorized by RGB, and then I got some contours. I think those are 1 foot contours overlaid against the classified point cloud kind of on the right there. So, it's not always, all this data is not always going into that GIS environment. There's a lot of engineering and surveying type applications that we're looking at with this specific system that we're flying. I think, in my opinion, the drone technology fits perfectly into these types of applications from a size standpoint. So, One thing is, we're not able to fly directly over the road, which we don't need to in order to capture usable data. We can fly offset to that. Utility applications, once again, this has probably been a big component for Ayres, acquiring a drone LiDAR system, is the ability to map utilities. So gives you an idea what that looks like, level of detail in the point cloud, as well as the vectorization for, you got the substation here, as well as the shield wires and conductors and all the different information around that substation. So, level of detail, just a typical, I think on this project, typical flight height for our system, we were flying, I think, right around 60 meters AGL. I think flight speed was, I think, 5 meters per second forward. And at those flight parameters, and obviously those change per project, we were getting in the neighborhood of 80 to 100 points per square meter. So this is kind of the moment, I guess, in my presentation that I like to point out that there's a lot of people out there right now generating point clouds from aerial imagery, from photogrammetry, and calling that point cloud information LiDAR. I guess the one thing I just want to do is just kind of point out that there are differences between the two, just to make people aware of that. As you jump into this technology, that there's a lot of terminology that gets thrown around. So I just hopefully want to clarify some of that. Aerial LiDAR, I think, as everyone's well aware, was developed from complex manned systems in the early 2000s. Ayres as a company, I think we got into fixed wing LiDAR around the 2003 timeframe. So we've seen a lot of bumps in the road in regards to processing of the data. I would say the biggest thing that's changed in that is post-processing of the data. A lot of our ground routines and brake line extraction routines and things like that have gotten a lot better. So UAV platforms are going to offer maybe a little bit more cost-effective solution for both imagery and potentially video acquisition. And then LiDAR generated point clouds are really are quite different than a imagery derived point cloud. This term dense image matching or pixel matching, some of you may have heard it referred to as pixel matching, structure from motion. There's all kinds of terminology, but what it is generating that point cloud from overlapping stereo images. Gives you an idea some of the unique attributes associated with each. You have that dense image matching point cloud. Once again, it's coming from an image-based platform, so that's a passive sensor. It has no ability to penetrate vegetation. LiDAR is an active sensor, so it comes from light. If you're standing on the ground in a heavy, dense, vegetated environment, you look up, if you can see light, it can typically be mapped from LiDAR. So, there's a lot of people out there right now flying drones or UAS that are capturing imagery and generating those point clouds. From the LiDAR standpoint, there's quite a few people right now considering that migration over to drone LiDAR. What's the cost associated with it? There's a lot of different systems out there that we kind of took a look at in the last probably year to year and a half, educated ourselves on maybe what's the advantages and disadvantages of each. Some more differences between the two. One's based on pixel resolution and one's based on point density. I think that last bullet really is that's where in the confusion lies, I think. The format of the files themselves are the same, but there's a lot of attribution that's missing from that image derived point cloud. So your image matching file, I guess, point cloud, if you're looking at that within a software that you can see this attribution, you'll see that you have one return. that only return. And then you also have a RGB value, obviously, that gets applied from the ortho image that gets captured as well. If you were to compare that against LiDAR, you have obviously multiple returns, first, last, first of many, last of many. You also have a point color. And when I say point color, that's really an intensity value. I mentioned intensity being the strength with which that pulse strikes a specific object. That gets recorded in every pulse that gets recorded. Gives you an idea of the two. That image-derived point cloud obviously has, once again, the RGB values associated with it. One thing, if you look at that image on the left, you can kind of see the data voids around the building. So any displacement in the building, you're gonna, if the image is not acquired with the proper amount of overlap, you're going to get voids in the data, voids in your information. Once again, a side-by-side comparison between that image-derived point cloud as well as LiDAR. This was not I don't think this was a UAS, captured point cloud. This is, I think, was a county-wide, but it gives you an idea what that image looks like on the left. You can kind of see, once again, you got some of those voids going on where you have vegetation. And then with LiDAR, obviously, you're going to be able to penetrate that vegetation just since it's a active sensor. This really tells the truth here, I think, with when you start drawing profiles on the data and looking at how, what kind of noise you had within the data set. And it really starts to show itself kind of on these hard surface areas. You can kind of see in the center of the screen there, the up and down nature of the point cloud on that hard surface. And what that ultimately translates to is inaccurate vertical information. You compare that against LiDAR, and you have a much more repeatable elevation from on the road. So those returns are coming in contact with the road, but they're ultimately not bouncing around necessarily. They're coming in contact with the road and returning back to the sensor. So there's much less vertical difference between those points from a LiDAR system than there are when you're deriving the points from an image. Once again, just some data voids in the data. Pixel matching is, and I know it seems like I'm probably hammering on the pixel correlation or the pixel matching as if it's not a good technology, and that's absolutely not true. It's just, it has to be the right environment to utilize that technology. If you have any type of vegetation, like we do on the left there, you're not going to get values, you're not going to get information within those vegetated areas. So I guess you have to decide how important is it in these soft surface vegetated areas to have elevation data, because if you need to go and fill those in with either field survey or possibly photogrammetry, how time intensive is that going to be and what's it going to cost? Once again, just a profile on a road from a LiDAR derived point cloud. Here's those same scenarios. Like to point out, those voids in the image match point cloud in comparison against the LiDAR. I'm going to kind of step through these. I don't want to push up against time, and I want to make sure we're leaving plenty of time for questions. One thing in regards to, this does not necessarily matter if it's a UAS or a drone LiDAR mission. It could be a fixed wing aircraft, could be helicopter or mobile LiDAR. One thing that's not discussed enough is the importance of doing manual review and manual editing on your data. I can write a macro to filter out the ground surface, from an automated fashion. It doesn't mean that my macro is good in all different terrain types. There needs to be a manual review where you have someone, generating a surface model and looking for those inconsistencies within the data that needs to be cleaned up. I think the last bullet there, design your post-processing methodology with your final deliverables in mind. You know, that's always, you have to start with those final deliverables and work your way backwards. Once again, some more cross sections on some image derived point cloud, just to give an idea. In heavy vegetation, how you're not getting data within those areas. And then you have that same area with Lidar, you know, being penetrated. You have, you know, a very consistent ground surface underneath the tree canopy, as well as those different returns off the top of the canopy itself. Kind of scroll through these. So, you know, this goes back to, you know, what technology is right for my project? You know, you have to ask yourself, you know, am I going to use drone photogrammetry? Is it just going to be airborne Lidar, drone Lidar? You know, what's the right technology for the specific deliverable that I'm trying to create? You know, each one has its advantages and disadvantages. You can kind of see some of the typical applications once again on the right there. You know, the one thing I think, my slide's probably a little bit out of date here, but in regards to airborne Lidar, specifically related to manned aircraft, those costs continue to come down just like everything else. Once again, if you're, you know, flying at the 30 point per square meter county-wide, you know, that maybe doesn't necessarily apply. But some of the lower resolution data sets, the cost is coming down. So when to use both? When am I going to use, you know, photogrammetry or imagery derived point cloud? And when am I going to use Lidar? You know, really the ideal scenario is to use the imagery for the context or interpretation, and then rely on the Lidar point cloud for the 3D component of your project. Both of those, you know, whether it be drones, manned aircraft, once again, Lidar and photogrammetry are really both powerful tools and are really full of a ton of potential when the projects are designed the right way. I think now that we've introduced the drones into this, I guess, space, you know, now you're offering a platform that's maybe much more economical from a collection standpoint. And I'm not going to read through all of this, I think, but as you get into looking at, you know, drones and Lidar and the different technologies, so photogrammetry, everything associated with this, I guess you have to ask the right questions and know what you're getting into. I think we've seen it, you know, with various people that have approached us, and they thought they were getting Lidar, and they got a elevation data set that was a photogrammetry or an image derived point cloud. And it maybe they were a little disappointed, maybe because there's vegetation on the site and they didn't have penetration through that vegetation, or it didn't meet their accuracy requirements. So I think that's all of my slides. I wanted to leave a few minutes, and I wanted to make sure I gave Dick plenty of time as well to get set up. But I guess thank you for the chance once again to speak at WLIA.
Yeah, thank you, Matt. I think that was a great presentation. I definitely appreciate you kind of explaining the difference between Lidar point clouds and photogrammetry point clouds, because I think that is something that's kind of a common misconception within the industry. So great job. We don't have any questions in the chat just yet, but we do have 5 minutes for questions. So if anybody wants to hop off mute and ask some questions, please go ahead.
I have a question. What is, I guess, do you have a way that you, I guess, determine vertical accuracy when you are doing a UAS flight?
So vertical accuracy, the best way to determine that is you have to have a data set of higher accuracy in order to check it against. So if I'm checking a Lidar point cloud, I have to check it against traditional field survey that's captured, you know, either GPS or total station. I can't check it against a lower accuracy data set. So in the case of Lidar, you know, or even photogrammetry, typically that's going to be field survey.
Hey, Matt, how long does your QA QC process usually take when you're looking at your LiDAR returns? Trying to clean them up.
Well, I mean, on a drone project, Nick, with a,
Yeah.
you know, typically from if it's I would say a couple 100-acre site, calibration would typically be on the data, a couple days, 2 to 3 days potentially. Then we have a process where we run an automated ground routine, where we'd also do as part of that a manual review, and then if we need to extract any break lines as part of that, we do that, and then final deliverables are typically created from that. But I would say on a couple 100-acre site, depending on the terrain, 2 weeks.
Awesome. Any other questions for Matt from the group? If not, I want to say thank you once again, Matt, and I appreciate your guys' presentation. Before we move on to Dick, we're going to have Chris play a couple sponsor slides. Thanks, Matt.